The goal of this experiment was to investigate how different factors control the release of a drug into the body from hydrogel beads. The drug was simulated by tartrazine, an organic dye with a peak absorbance at about 427 nanometers, and the body was simulated simply as a known volume of deionized water. The dye was delivered from sodium alginate beads, which allows the dye to diffuse slowly from the bead and into the simulated body. By measuring the absorbance of the water at 427 nanometers, the amount of dye released over time can be calculated based on a calibration curve. Of particular interest is the fraction of drug delivered, F, which is defined as the ratio of mass of drug delivered at time t, mt, versus drug delivered at t equals infinity, m infinity. This experiment specifically looked at how bead size and agitation rate of the receiving water affect drug delivery. The governing equation for this system is as follows. F, the fraction of drug delivered, equals K, a constant which depends on the interactions between the polymer and the drug, times T to the power N, where N is the diffusional exponent. For ideal, non-swelling controlled diffusion from spheres, N should be equal to 0.43. This is the region known as Fickian diffusion, and represents classical ideal molecular diffusion. Values of N greater than 0.43 indicate that non-Fickian diffusion is occurring. N greater than 0.85 indicates that the diffusion is swelling controlled, meaning the change in size of the beads as they absorb water has a large effect on the rate of diffusion. Also note that factors like particle size distribution can have an effect on the calculated values of N. N and K can be calculated easily from experimental data. Taking the natural log of both sides of the governing equation yields an equation that is linear in form. By performing a linear regression of the experimental data, specifically the natural log of F versus the natural log of T, N will be the slope of this line, and K can be obtained by exponentiating the y-intercept.
Create 1 liter of a solution that is 0.5 gram per liter tartrazine in DI water. Make alginate solution. Add 0.1 gram per 10 milliliter of 0.5 gram per liter tartrazine solution. We need about 300 milliliter of solution. Stir until a smooth, uniform yellow solution is formed. Prepare 500 milliliter stock solution of 6% calcium chloride. Carefully put the calcium chloride solution into a large weight bowl. Load 3 milliliter alginate into a disposable syringe by immersing the tip of the syringe into the solution and pulling back on the plunger. Slowly dispense the alginate into the weight bowl containing the calcium chloride stock solution. Make sure to record the cross-linking time about 5 minutes. Push slowly enough to assure drop-wise dispensing into the calcium chloride. Avoid drops falling on the top of other drops. Immediately separate the beads from the calcium chloride solution by filtration. Rinse the beads with DI water after filtration. Fill a 150 milliliter beaker with a 100 milliliter DI water. Add the alginate beads into DI water and start stirring with the magnetic stir bar. Remove samples with a pipette every 2 minutes for the first 10 minutes, every 5 minutes for the next 20 minutes, and every 10 minutes for the last 30 minutes. And measure the absorbance with the spectrophotometer. Return the samples to the beaker after measurement to maintain the constant volume.
This is just time versus absorbance at 427 nanometers. And as you can see here in this 300 RPM graph, the needle sizes aren't really in any particular orders. This could be due to some error in the experiment. And then for this graph, you can definitely see that there's more of a trend where you have the larger beads as the top line here, and then it gets smaller as you go down. And this is the 22 gauge needle versus spin rate, because this is the only needle that we tested at 700 RPM. And as you can see, the trend is 700 RPM is at the top and the 300 RPM is at the bottom with the 500 line in the middle. and that follows a trend like we would expect. In order to get our data into any useful sort of form, we use this calibration curve where we took different concentrations of our solution and we put measuring the absorbance at 427 nanometers to compare it to molarity. Using the trend line that we got here, you can plug in an absorbance and get out a molarity and convert all of the other data. So this is the F versus time graph for the 300 RPM with varying needle sizes. And what this graph shows is F, which is the fraction of tartrazine leaving the hydrogel bead, versus time. So it has a polynomial-like curve. So as you can see, there's no real distinct trend. Lines kind of overlap, and there's nothing really that we can see here. And for the 500 RPM graph, there's more of a distinct trend with the 22 gauge needle here on the top, the 16 gauge needle here in the middle, and the no needle trial here on the bottom. And then here for the 22 gauge at the 700 RPM, you can see we have a similar trend. So these are the important graphs here. This is the ln of F versus the ln of time. So for 300 RPM, took this first 60% of the data, so up to 30 minutes, and we graph them with these linear trend lines. So these linear trend lines show us two very important things. The slope, which is the n value, and the n value is what type of diffusion is happening in the system, and then the exponential of the y-intercept here is the k value, and the k value is a constant, and it should be relatively similar between trials of the same speed. And we see 500 RPM, and this is the 700 RPM graph. So here's where we have the important data analysis going on. So we see that we have different n values for the different speeds and the different k values, and we also have the errors for all of them. So the linear trend lines you saw in the previous graphs had different n and k values than these ones because we decided to analyze our data for this a little bit differently. In order to get the standard deviation, we had to take the n and k value for each individual trial, then average them. So the graphs you saw before were just the averaged F values, and then we found the N and the K. So as you can see here, we have very low error, and we only get Fickian diffusion, really. We get it close here at the 300 RPM no needle, and we get Fickian diffusion at the no needle for 500 RPM and the 16 gauge. And as you can see, the K values are really consistent, which shows us that we did something right with our data. But again, like I said, the trends are all kind of funny. We think that an error that could have happened in data collection is when you're dispensing beads, you're attempting to ensure that the beads don't drop on top of each other, but there's no way to make sure that this happens in reality. So if a bead were to drop on top of another bead, they essentially fuse together and change the surface area to volume ratio, which changes the diffusion rate. And then we also have another problem using the syringe. We can't measure exactly 3 milliliters as accurately as we would like, so we may be using different volumes of beads for each trial. We could see this because we recorded and we actually wrote down the number of beads for each trial that we dispensed, and it was different for each of the trials, even with the same needle size. And another problem with the needles is that we, attempted to do drop-wise dispensing, but you need to dispense the beads quickly so that they all have a cross-linking time of 5 minutes or close to it. It is possible that we weren't dispensing beads too quickly, or they were formed with different radiuses and it changes the surface to volume ratio.